In this video, we will discuss about the types of AC power. Here, three types of powers: AC power, real power, reactive power, apparent power. The AC power. To know the AC power, we should know about what is AC impedance. AC impedance is a complex quantity made up of real resistance and imaginary reactance. So Z equals to R plus Jx. The units is ohms, where R is resistance, X is imaginary reactance. AC apparent power is a complex quantity made up of real active power and imaginary reactive power that is denoted by S equals to P plus JQ volt amperes. Now we will study what is AC active power, that is real power. It is denoted by capital P. The active power is the power that is dissipated in the resistance of the load. It uses the same formula used for DC. That is, voltage and current are the magnitudes, not the phasors. A mathematical expression is given by P equals to I square R, that equals to V square by R. The units is watts. Here with AC power calculations, one note: the voltage in the above equation is the voltage drop across the resistor, not across the entire circuit. Real value of resistance R is used in real power calculations, not impedance Z. Next, we will study about the reactive power denoted by Q. That is the AC imaginary reactive power denoted by Q. The reactive power is the power that is exchanged between reactive components, that is inductors and capacitors. The formulas look similar to those used by the active power but uses reactance instead of resistance. Here Q equals to I square X, that is equals to V square by X, that is volt ampere reactive. So unit is volt amperes reactive VAR. Q is negative for capacitor by convention and positive for inductor, just like X is negative for capacitor, that is given by minus JXE. Note here, for AC power calculations, the voltage in the above equation is the voltage drop across the reactance, not across the entire circuit. Then the AC apparent power is denoted by S. The apparent power is the power that appears to flow to the load. The magnitude of apparent power can be calculated using similar formulas to those for active or reactive power. S equals to VI, that is equals to I square by I square Z, that can be given by V square by Z, that units is volt amperes. V and I are the magnitudes, not the phasors. We can understand the real and reactive power by using power triangle. This power triangle also shows that we can find real power P and reactive power Q. So here S equals to VI volt amperes, P equals to S, that is nothing but VI cos theta watts, Q equals to VI sin theta volt ampere reactive. Note, the impedance angle and the power factor angle are the same value. Today we will discuss about the power factor and its importance. Today's class consists of introduction, definition, power factor correction, importance of power factor. Introduction. To understand power factor, we will first start with the definition of some basic terms. Kilowatt is working power, also called actual power or active power or real power. It is the power that actually powers the equipment and performs useful work. kVAR is the reactive power. It is the power that magnetic equipment, that is transformer, motor and relay, need to produce the magnetizing flux. kVA is the apparent power. It is the vectorial summation of kVAR and kW. Definition first, power factor can be defined like this also. It is the cosine of the phase angle between the applied voltage and resulting current of the circuit. So generally that is cos phi. Definition 2. It is defined as the ratio of resistance of the circuit to the impedance of the circuit. For purely resistive AC circuit, R equals to Z and the power factor equals to 1. So here power factor is cos phi is equals to the R divided by Z. That is resistance divided by the impedance of that circuit. Definition 3. Power factor is the ratio of active power to apparent power. So that is power factor equals to kW by kVA. The correct way to represent the power factor is the ratio of active power to apparent power. What causes low power factor? Since power factor is defined as the ratio of kilowatt to kVA, we see that lower power factor results when kilowatt is small in relation to kVA. What causes a large kVAR in a system? The answer is inductive loads. These inductive loads constitute a major portion of the power consumed in industrial complexes. Reactive power kVAR required by inductive loads increases the amount of apparent power kVA in your distribution system. To increase the reactive and apparent power results in a large angle theta. So measured kilowatt and kVA. As theta increases, cosine theta or power factor decreases as. Why we should improve power factor? Some of the benefits of improving power factor includes low utility fees, increased system capacity, and reduced system losses in your electrical system, increased voltage level in your electrical system, and cooler, more efficient motors. Power factor correction 1. We have seen that sources of reactive power, that is inductive loads, decreases the power factor. Similarly, consumers of reactive power increases power factor. Thus, it comes as no surprise that one way to increase power factor is to add capacitors to the system. This and other ways of increasing power factor are listed in the next slides. Power factor correction 2, that is installation capacitors, that is kVAR generators. By installing this one, the power factor can be increased. Power factor correction 3, that is minimizing operation of idling or lightly loaded motors. Third one is avoiding operations of equipment above its rated voltage. Next is the replacing standard motors as they burn out with energy efficient motors. Importance of power factor. A power factor is one or unity power factor is the goal of an electric utility company, since if the power factor is less than 1, they have to supply more current to the user for a given amount of power use. In so doing, they incur more line losses. They also must have larger capacity equipments in place than would be otherwise necessary. As a result, an industrial facilities will be charged a penalty if its power factor is much different from 1, that is unity. Another important power factors, industrial facilities tend to have a larger lagging power factor where the current lags the voltage like an inductor. This is primarily the result of having a lot of electric induction motors. The windings of motors act as inductors as seen by the power supply. Capacitors have the opposite effect and can compensate for the inductive motor windings. Some industrial sites will have large banks of capacitors strictly for the purpose of correcting the power factor back towards 1 to save on utility company charges.